Hi. Okay, this is using pose estimation to map gaze to detected fiducial markers for the EMDPa special session at KES 2020. I am Andrew Dachowski, and I'm at School of Computing Clemson. This was also joint work with Vsevolod Pejsakovic at Isaïe Soupero at University of Toulouse in Toulouse, France, and Christoph Kreitz in the psychology department at the SWPS University of Social Sciences and Humanities, Warsaw, Poland. So some of this work is in part funded by the U.S. National Science Foundation from myself and from the Polskie Ministerstwo Nauki i Szkolnictwa Wyższego in Poland for Krzysztof Kreitz. So the motivation here, what is this paper about, is really augmented reality registration. So that's the registration problem. And so if we have the little white dot that you see there, it shows up here, there, and there. On the video frames that we have when we collected data sitting in Toulouse in this cockpit, we're interested, for example, in counting gaze fixations on cockpit elements like we have here. And so the registration problem basically says, well, where is that dot, the gaze point, on the areas of interest, or AOIs, in the video? And so that's the question. And so what you see here and on the other frames is our fiducial marker, or for, oops, and I didn't do it in the right place there, but it's here. It's the Aruco marker, which I happen to like for augmented reality applications. Okay, and so fiducial markers are not new. They've been around for a while. If I remember correctly, VR Toolkit had them a long time ago. These days, you can find several different libraries. I happen to like Aruco because there's a nice web page to generate the Aruco markers. You can print them out, and they're fairly easy to get going from within OpenCV. You just have to install the some of the additional modules to get them to work. And we're obviously not the first ones to use it. Andrus et al. Had a CHI 2017 paper where they used that between human users and these avatars, and there were Aruco markers on the display, so we knew when a person was looking at the display or when either person or avatar was looking at a table, and it was a sandwich making task. Singh et al. Also talked about using markers for aviation uses, and in fact, just what we're trying to do here. But one thing that I've noticed is that oftentimes the markers, like you see in the picture below, that's from our ET4S paper a couple of years ago, before I had this, figured this little bit out that I'm going to present today. Oftentimes multiple markers are used simply because once you get the position of these guys, then you can draw the quad, and the quad will pretty much move, or the orientation will change. In other words, it'll rotate based on the position of the markers on the 2D plane. What I'd like to do, though, is each marker gives you, along with it, an X, Y, and Z axis. And so, or in the rotations along those, with respect to the camera view axis. And so the idea being is that you should be able to just use one marker to define a plane which is perpendicular to the camera. And then if you recover the rotations and translations from a single marker, then you should be able to do the same kind of orientation without the need for the other three. One may argue, okay, the other three are there for occlusion and things like that, but I wanted to see whether we can get the orientation from one marker like we have here. Now this also shows an ambiguity problem, which is still there, and I haven't quite figured this out yet. So if anybody else knows how to fix this, basically here the z-axis goes out, and here the z-axis goes in as it's supposed to. So this is due to ambiguity of whether the library thinks the Aruko marker is basically facing in or out. I'm not sure how to fix that yet. But anyhow, the point being is that you see an illustration here. Once you have one marker, you can define an AOI with respect to that one marker, change the dimensions. In fact, the markers, you know what dimensions they are. They're usually, you can print them out to be 10 centimeters or whatever. And in fact, you use that inside the code. And then if you have the physical dimensions of the picture here, then you should be able to map the AOI yourself very accurately, in fact, although it does degrade as you get away from the marker. So that's something else due to the distortions at play. Anyhow, the point being is I would like to use one marker to get the AOI and to also use the OpenGL reference frame and draw the box around the AOI using OpenGL instead of using OpenCV. All right, so how does this work? Well, we start with the X, Y, and Z coordinates in 3 space. And then we rotate and translate them. So these are the rotations in space relative to the camera view axis. And then also the translations here. So this is essentially, I always think of this in OpenGL kind of graphics way. And for OpenCV, it's kind of backwards. So in OpenGL, you always start with the object, let's say this pencil, and then you rotate and translate that object relative to the world origin. Here, it's slightly different. It's almost the reverse. You start with rotation of the thing that you're looking at in the camera with respect to the camera axis. So usually something there is dead on, so it'll be right here in the center, and if you rotate it and translate, then you can enact the rotation and translation of the object in 3 space on the 2D camera plane. The other thing you have to worry about here is essentially, well, I tend to think of them as fx and fy, the focal distance. So this is a scale parameter of the camera, of the lens really, and then cx, cy is the offset of, depending on where the 0, 0 origin of the image frame is. In eye tracking, oftentimes an eye tracker will give you the 0, 0 at the upper left. Sometimes 0, 0 is in the middle, however, and so you have to worry about this. So initially, you don't necessarily know what the camera matrix is, and so you have to recover this from OpenCV itself. So let's continue here. Usually what you do, this is during camera calibration, and so you either look these numbers up, so you were always trying to find these, and you either find those by looking them up, somebody's already done this for you, or you can do it yourself. And to do it yourself, essentially what you do is you assume that the points that you're going to be looking at with your camera lie on the plane, and so we can zero out the Z coordinate. For example, the chessboard is a very well often used kind of stimulus or picture where we present to the camera, we know the dimensions of the chessboard, and so all we have to figure out is how to solve this equation using those known points. So if we get rid of the Z coordinate there, what we end up with is the camera matrix as before, but now our rotation and translation is only in 2D. We don't care about rotation. Well, let's see, I guess it would be mostly about Z. That's a good question. I'm not sure whether it's rotated about Z. It's not rotated about Z. All right, the thing lies in the plane, so you have to do a couple of views to solve for the matrix. So let's continue with this. You just need the plane, 3 views of it with 4 known points on the plane to solve this. And right, it's rotate X, rotate Y. I guess we don't worry about rotate Z. So here's an example of how that would work. And this is pretty much built in to OpenCV. There are routines that are already built in, and see the paper for how to do this. You just need to present 3 views, and here I'm not rotating around Z, but I am rotating X, and I think I'm rotating about Y, really. Rotate X would be, I guess, this way. So you don't want to rotate Z, or this way, it would be rotate Z. So rotate X, rotate Y, and not rotate Z. So yeah, and all you need is 3 views in the code. If I have the examples sort of like in tutorial form in the paper, where you can see how those 3 views are captured. The error is reduced the more views that you get. And what you end up with is the camera matrix, and more importantly also, which I don't have in the equations before, but the distortion coefficients D, and they're either pin cushion or the other one. It's either radial or fisheye, I believe. So most cameras, or lenses rather, will have a little bit of distortion that you have to obtain used from this. So OpenCV will give those to you, or you can look them up. A lot of the camera manufacturers or lens manufacturers already have those. So once we have this, those are called the camera intrinsics. We have K and D. Then all we need is the rotation of, let's say, this marker relative to the camera. And so you can see that we would have gotten a translation. So this would be TX and then TY, translation. And then you can see that the original box that was here would have been rotated a little bit, so we can recover the rotations. So all those transformations, we get the R, rotation, with respect to the camera, and translation, how far away off axis it is. And if we have that, then we can project the points that are relative to this marker, like this one here, and that one there, and so forth. Those are relative, and so we just project those 3D points, because you got to remember that initially what we have is the original marker sitting here, then the other markers would be relative to it. We can draw them this way. And then they all undergo the same rotation and translation as the main one, right? So as long as that one is, so they all rotate a little bit and they all translate a little bit with respect to the on-axis view of the camera. And the boxes here are drawn using OpenCV. And that's one thing that I don't happen to like, because I like trying to take control of the graphics and using OpenGL, which is, I think, a bit more powerful graphics library to draw my own things in 3D. And so it's a matter of lining up the things in 3D with the information that we have in the camera reference frame. And the gate spin is already in 2D, so that's nice. So what we have here is using OpenGL. And so for OpenGL, what we have here is the rotation and translation of some point in 3D space. And essentially what we do is we can use this directly from OpenCV and construct our rotation and translation matrix. Actually, there's a couple of negations they have to do, because Um, the rotation and translation is with respect to the camera, whereas in 3D world coordinates, there's a couple of minus signs that you got to throw in there. I think I have those specifically in the paper. And then what you end up with is essentially our traditional homogeneous coordinate model view matrix, as it's called. And so after the model view matrix, all we need is the M projection matrix, which we get from the camera intrinsics. So there are two matrices that we need. We've got one, and now we're going to work on the next one. And the next one is basically the NDC here and the KGL multiplication, which gives you this. So all these values in here in the projection matrix have to do with the camera intrinsics, fx, fy, cx, cy. And then the other values are our width and height of our 3D space, so of our view frustum. So basically we get width, height, and then where this is the front plane, and then the back one is sorry, that's the near plane, N over here, and that's the far plane. So Fn, width and height specify the view frustum in 3 space for OpenGL. And with that, we have the projection of the 3D object into 2D space, and then all we have to do is then transform the remaining 2D using the same transformation that we had here. And this is all courtesy of Amy Tabb, who's got a really nice web page about this. And that's where I got it, and I essentially put that into the code. So this projection matrix is pretty much hard coded. Of course, you have to know the fx, fy, cx, cy values to put them in there. All right, so this allows us to draw just slightly nicer AOIs, as in this case. So here, I've just drawn circles as opposed to squares. It's not a big deal, but it just shows you that you could draw just about anything now. I could have drawn teapots if I wanted to, as is common in graphics. And then we have a very nice 3D kind of possibility of drawing 3D AOIs if we wanted to, or still keep them 2D. Doesn't matter, depending on whatever you want to do. There's only one problem with this, though, and that is that the AOI membership test still has to be done in the image reference frame because the gaze point is still in 2D, and I haven't figured out how to project the 2D gaze point to 3D. What we would end up getting, which I don't have yet, but if in the yellow here is the gaze point, what we'd have is something like, I don't know, maybe 2 rays that come in from the user or something like that and intersect at that gaze point. Or something like that for the left eye, right eye kind of rays, but I don't have that done yet, and I'm not sure exactly how to do it, but that'll be the next step. So it's kind of it's the best of both worlds. We could use OpenGL to draw fancy graphics, but still use OpenCV and the image reference frame to do our 2D AOI point in polygon membership test. And so here's what it looks like when you run it, and it still has that ambiguity problem where you can see the z-axis, the blue axis, is flipping on me, which I still would like to get fixed, but I don't quite know how to do. All right, so that essentially is what all the paper is about. It's not anything particularly new per se, but it is all in one place for you to look at and to implement yourself if you want to go this route and use OpenCV in combination with OpenGL to draw nice graphics. And there's still work remaining here to do something with gaze vector projection into 3D, which I think would be really cool. All right, if you have any questions, I'll be happy to answer them in the I guess, simuli portion of the conference. Thank you so much.